Wow. Okay, let's get going. So I'm Cliff Pollack. I'm going to be filling in for Deb Deep for a couple lectures now. I hope this transition is not too awkward. I always hated it when it's a change because there's a different rhythm and all that kind of stuff. So if there's any trouble, let me know. You know, if you don't follow something or if he uses different terms than I do, just tell me, and we'll try and make this thing fairly seamless to the degree we can. So he said you've got up to beam diffraction. So I'm going to cover beam diffraction and coherence, and then we're going to start the ray tracing, the ABCD matrix stuff today, I hope. And then the next few days we're going to do the ABCD matrix and go through all the how do you design a resonator and take it from there. So let's start with beam diffraction. Beam diffraction is it happens in any sort of beam, any sort of wave spreads. That's diffraction. And so we wanted to establish a theory for that. What we do in optics is we use the plane wave as a model. It's like it's a building block of all phenomena. So let's start with a plane wave. A plane wave is something which is traveling in a certain direction, represented by a k vector, and it extends from minus infinity to infinity. So it goes down here, it goes up to here, it goes on forever. This is perfectly flat wave, and of course it's this wave, so there's a series of waves behind it, and it's propagating in a particular direction, in only one direction. So plane waves don't exist, you know, nothing goes to infinity or not, but they form a basis set for ways we can describe them. And we describe this thing as traveling with an electric field amplitude, which looks like some sort of amplitude, e to the j, k, z minus omega t. K is a vector. K tells the direction of the vector, tells you which way you're going. And the magnitude of k is basically a spatial frequency. It has units of radians per length, per centimeter, let's say. So it tells you how much phase is accumulated per unit length. Omega, of course, you know omega. Omega is an angular frequency. It tells you the radians per second. So radians per second times time, radians per centimeter times distance tells you the phase everywhere. Anyway, there's your plane wave. We use this as our model. We use it for our building block for all things. Now, it doesn't exist. What does exist is real waves. And so I fortunately have a real wave here. Here's a laser. Thank you. So there's a real wave. What do we see about it? It's certainly directional. It's going in one direction. But it's certainly not infinite, is it? You know, it extends about a millimeter or two, and then it's done. So a real wave, it does not look like a plane wave. But we can use plane waves to describe what this wave looks like. And what we do is we make a superposition of plane waves. So we take one plane wave, clearly going like that, and we'll add to it maybe one like that, and one like this, and one like this. And we'll make a superposition of these things, just like you do in Fourier transforms. If you want to make a short pulse in time, you take a whole bunch of frequencies, which are infinite in extent. You know, they go on forever, but you sum up all these little frequencies and make a Fourier composition to make a little pulse. So a short pulse in time, usually a lot of frequencies involved. Well, spatially, if I've got a little beam which has a spatial extent like this, so here's 0, and here's say y, it doesn't go to infinity. The way I deal with it is I take a plane wave going this way and add some like this and some like that, and add them together, and then if I add enough of them together, I get this spatially confined mode. So this is an interesting demonstration. These are all coming out the same wavelength, but the k vector, these beams can go up. There's k plus 90, there's k flat, there's k minus 90. I can vary k all over the place, even though I've got the same wavelength and frequency. So these plane waves, they all might have the same exact wavelength. They just have different directions. So they are distinct because they have different k vectors. So you take them, add them together, and form this superposition. And so basically, mathematically what we say is, well, E of x, or E of y, if you will, is going to be some sort of superposition of E of k dk times some amplitude, A of k, over k from minus 90 degrees to k to plus 90 degrees. So in the k vector, magnitude stays the same. It's just the orientation of it. So that's all we're doing with the real wave. We're going to model it as a superposition of plane waves. Now, once you've got that model, that explains, a lot of things. If we let this wave propagate now, so I've got this wave, and I've got this thing here. I take my plane waves, I add them all together, I get a little beam. So right here, I've got my beam. It has a spatial spread like that. Here's my y-axis. I'm going to let it propagate. So I go here, and I say, okay, this is actually a superposition of some plane waves. And they have different amplitudes and stuff, but they go in their own way. Well, each plane wave, they're all independent, so they're all just going to go along on their own, travel by themselves. And so each of these is going to spread out. And one's going to go up here, one's going to go here. So you can kind of see just naturally what's happening as a beam propagates. If it's got k vectors which are not all along the z-axis, they're going to spread. So the beam spreads. And that's all there is to it. So we go down some distance, and these guys have spread, and now my beam, which was here, now looks a little more like this. It's enlarged. And that's called diffraction. And that's always going to happen, because any beam I make is going to have a superposition of transverse k vectors. If I make it bigger, I don't need as many, but I still have some transverse wave vectors. That's going to spread. Make it bigger, fine, it's still going to spread. Not as fast, but they spread. So all beams spread. That's all there is to it. A second thing you see out of this is, if they all started here and they propagated, they all go at the same time, they're going to arrive just a little bit shy of each other, and we're going to get some curvature in the wavefront. So not only does this wave travel along, it maybe starts as a plane wave here, or flat wave, but it starts developing some curvature as it propagates, as well as spreading. So this is a characteristic of all waves. How much does it spread? If you look at this Fourier transform, this is kind of a Fourier transform converting these things. If I had a beam which was, let's say we had a Gaussian beam, for example, if E of y, and why do I use a Gaussian beam? Because laser beams tend to be Gaussian. We're going to see a lot of Gaussian beams, so you might as well just start using them. If this was equal to something like this, E naught e to the minus y over, let's call it omega naught squared, where omega naught is just a characteristic length. That has a distribution which looks Gaussian. That's going to have a E of k, which has got a whole bunch of constants, square root of pi, omega naught, E naught, and then e to the minus k sub y squared omega naught over 2. Oops, k sub y omega naught over 2 squared. Okay. So it's going to have a Gaussian distribution in k space as well. But it's going to have these y components. It has the major component of k is there, but there's a y component. And this is, notice as ky gets bigger, this amplitude gets smaller. So we're going to have a distribution of k vectors, which is also Gaussian. And at the 1 over e point in k space, you're going to have an amplitude of, what's it going to be here? 2 over omega naught. So that's going to be the kind of the average extent of my transverse k vectors. So when I make this superposition, wherever it was, I've got my major one just pointing in the direction I want. That's just k, and then I'm going to add, let's call it kz, and I'm going to add some other vectors to it. And probably the biggest one, I'm going to have kz going along here, and then I'll have some ky over here, and that's going to have a value of what did I have here? Omega 2 over omega naught. So that gives you a sense how much the beam is spreading. And so from these two things, I can figure out my diffraction angle. Angle is just the tangent of the opposite over adjacent. So my angle theta is just going to be 2 over omega naught divided by kz. Have you talked about k yet? Do you know what k is? We gave you some numbers here. Spatial frequency. One of the units of k is 2 pi over lambda. So if I have a k, if I have a wavelength lambda, then the k vector is 2 pi. That's how much phase it accumulates per distance. So you can rework this, and you get this is equal to lambda over pi omega naught. So that is the angle here at which that diffracts. And of course, that's just the top half of the beam. It also diffracts downwardly. So the full diffraction angle, theta full, is 2 lambda over pi omega naught. So long wavelength, the beam spreads a lot. Big beam, the beam doesn't spread so much. So the bigger the beam, the less the diffraction. The shorter the wavelength, the less the diffraction. So microwaves, you see these big microwave towers with great big antennas. They have fairly long wavelengths, so a big dish to make it a big spot size to keep it kind of collimated. Laser beams, much shorter wavelength, they barely spread because it's a very short lambda is very small here. But here omega naught's on the order of a millimeter, it still spreads. You know, I don't know how big it is. It looks like it's about 3 millimeters. I don't know how far it goes if I come back. I'm sure it's going to be bigger than that from here. Oh yeah, so you can see it spreading. So everything spreads. And the smaller you make the beam initially, the more it spreads. So we'll talk a lot about that as we get into the cavities.
Sorry, what was omega naught again?
Omega naught is the characteristic half size of our Gaussian beam. So that'd be where it's the 1 over e point of our beam. We'll talk more about omega naught, but turns out a Gaussian beam, we're getting way ahead, but a Gaussian beam has an intensity profile, has an electric field which is Gaussian. So E is kind of some amplitude, e to the minus y squared over omega naught squared. And omega naught is some characteristic distance. Turns out when you look at it, your eye is kind of a logarithmic response. If you look at that laser beam, if you look at that, you can kind of see a spot there. If I asked you to tell me how big that is, you can go up there and you could draw a line around it. And what you find is when you draw the line around these things, you're going to tend to kind of pick that point right about there. It's really funny. Your eye kind of goes for the 10% point, and you draw the line there. That turns out to be, this is electric field amplitude. When you square it, you get a 2 there. That turns out to be the omega naught of intensity. So it's kind of funny, but so you can look at a laser beam on the wall and pretty quickly, get a pretty good idea what omega naught is by looking at it. If you just go up, it's hard because it's fuzzy, but just kind of put a circle where you say the beam is, and you will be very close to accurate. But we'll talk more about omega naughts and Gaussians and all that, or maybe deep will. We'll talk a lot about the Gaussian beam characteristics. So all I just wanted to point out here was that beam spread, why do they spread? Is because there's a superposition of k vectors when you put them together. And the plane waves are idealized systems. They're a basis set. They don't really exist, but it's a basis set. They're perfect, and we can describe things in terms of that basis set and make nice calculations. So that's that. Something which I think is kind of fun. If I were to take an aperture, instead of taking a laser beam, let's take a plane wave. So I'll get one of these ideal plane waves. And it's cruising along, happy as a clam. It's going one direction. I'm going to put an aperture here. What's the field look like way beyond there? So what you have at this point here, if I looked at the electric field at this point, I would find I have, I'll do it up here. I have 0 intensity, full intensity, 0 intensity. So this is my electric field. So suddenly I've got just this little piece of field here, and now I'm going to let that propagate. Now, we can go through the analysis if you want. It's pretty easy to do, but the simplest way to do it is just to divide this into a bunch of points. Kind of put a separate, take 2 dipoles, half the distance apart, and look at the pattern for that. And then move it and just make a superposition of those things. If I take 2 dipoles here and propagate them, what you see is you're going to get an interference pattern over here, which, when you look at the intensity, looks like a sinc function, and so forth. And so when I have a square like this, I get a sinc function. what's the relation between that and a sinc function?
Fourier transform.
It's a Fourier transform. And so one of the neat things about diffraction is that I've got my aperture, whatever my system is at the aperture, if I let it go to the far field, the beam looks like the Fourier transform of my aperture. So this is something we'll also use. Beams, optics is there's something called Fourier optics. And it's natural evolution. As the beam propagates, it becomes the Fourier transform of itself in the far field. So if I start with a Gaussian here, what's the Fourier transform of a Gaussian? It's a Gaussian, right? So a Gaussian beam remains Gaussian. And that's very nice. That's in fact why lasers tend to be Gaussian beams. They're kind of self-consistent systems. But a square aperture, the Fourier transform is a sinc function. And if you take a slit and you shine light on it, you'll see kind of a sinc function in your interference pattern, and so forth. So this issue of beam propagation, diffraction, Fourier transforms, curvature, spreading, all these things are kind of self-consistent with a wave as it propagates. And we will see these things as we develop a more consistent description of the beam. Any questions about that? We'll revisit a lot of this stuff. All right, just a few more tidbits to finish up. One was the Brewster Angle, and we use that a lot in lasers. I'm sure you've seen it before. But if you take Maxwell's equations and you apply the boundary conditions, you say I've got this interface, and let's let this be air and this be glass. And so I'm going to bring a beam in at some angle of incidence. This beam can be polarized in the plane or it can be polarized out of the plane. So here's my electric field. My electric field can be like this or it can be like that. It's two cases. And you can solve the boundary condition. And you use Snell's law and you say, okay, it goes through and there's a reflection. And depending on signs and stuff, we can compute the transmission and reflection and all that kind of stuff. And I'll let you do that on your own or look it up sometime. But what you'll find is that if we are polarized like this out of the board, that's called S polarization, you get your transmitted field over the incident field looks like this. You get 2 n1 cosine theta incident over, oops, okay. And let me do it this way. n1, n2. I'm sorry about this. So 2 n1 over n1 cosine theta incident plus n2 cosine theta transmitted. So here's theta incident, here's theta transmitted. So you get this fairly nice thing like this. If you polarize like this in the plane, parallel to the plane of incidence, that's called p-polarized, then you get a different formula. And it looks like this. It's n1 cosine theta transmitted minus n2 cosine theta incident over the sum. Okay, so what? Let's plot it. If you plot this as a function of theta incident, and I'm going to plot the magnitude of the transmitted beam, it actually goes off, it flips sign here. It goes from a negative through 0 and up to 100%. So here's 100% at 90 degrees, or not, yeah, 90 degrees. So the transmission, I mean, you get some transmission here. What am I? I'm plotting reflection. God, I'm just screwing up. This is E reflection. Yeah, sorry. I'm sorry. So if you look at the reflected light off this interface, I'm looking at this thing here. It flips sign. It starts as a negative and then goes up like that. And there's a point where it crosses the 0. And there's no reflection. So there's one particular angle where there's no reflection off the surface. And that happens at the point where the tangent of theta equals n2 over n1. That's called the Brewster angle. And so there's a way to get light through a surface with no reflection. And so we use that a lot in lasers. You know, your gain medium very often will look like this. It'll be a rod, long rod, which we want to go through, but that's cut at a Brewster angle so that the light will come in like this, hit a Brewster angle, go through, and then leave. And there's no loss at all. So it's the ideal way to make a perfect low loss interface for light into a system. So we're going to try and have you build a, I was thinking about this last night. Either we're going to have you build a Ti-sapphire laser or maybe a chrome zinc selenide laser. So we'll give you a crystal. And we're going to give you a bunch of mirrors and a pump laser. And we're going to say, build the laser. You got to design it, and you got to go in and build it. But the crystals we have are not coated. So they have to be put in the beam at Brewster angle to have zero reflectivity, zero loss, perfect transmission. So you use Brewster angle as you build things. Yeah?
Yeah, sorry. What does S&P stand for again?
Senkrecht parallel. It's German. Senkrecht, who's German here? That means transverse. Parallel means parallel. So you've got a plane of incidence. Here's my plane of incidence. Here's my normal. I'm coming in like that. This is the plane of incidence. If I'm senkrecht to it, I'm transverse. If I'm parallel to the plane, I'm parallel to it. So my electric field's either like this, or it's sticking out like that.
So that's the P case.
That's the P case. That's the P case, yeah. And Brewster angle is P case. So the not so cool thing about Brewster angle, well, it depends on your attitude. You can have a polarized laser. This laser is going to operate in that polarization. And usually you want a polarized system, that's great. But there are times when, oh man, you know, the gain is higher in this mode, or if I can get both, you know, you're restricted to one polarization when you put a Brewster surface in. Usually that's a blessing, but you know, it's an issue you got to worry about. So a Brewster angle works like a charm so long as you got polarized light. You know, if I want to make light for my glasses, you know, I like anti-reflection coating on all my optics, but this only works for one polarization. So it's if you have unpolarized light, the Brewster angle is not very useful. But this is a nice trick. If you don't know what the polarization of is that light coming off that reflection polarized, play with the Brewster angle. You can take a piece of glass, and you know, if you can kill that reflection by tilting it, it's polarized. If you can't, it's not. So there's all sorts of Mr. Science you can do with this kind of stuff. So you'll see that in lab quite a bit. Yeah.
Isn't that just TE and TM?
That's TEM and you what?
Isn't that S polarized just TE and P polarized TM?
Yeah, we call it TE and TM if you want as well. In a waveguide, there's transverse electric and transverse magnetic. But in free space, we call it S and P. So, all right. So the last tidbit we have is coherence before we get to the fun stuff. So I consider all this kind of background. You know, we'll learn it as you go along, but let's talk about it formally. So coherence is a word which is used to characterize the laser. That was when it first came out. It was a coherent source. Everybody's excited about it. What does that mean? So coherence just means things are in phase. There's two types of coherence. One is I've got spatial coherence. So you've got some wave cruising along. Let's look at the wave front, not the rays, the beams, the wave front. So I've got some wave front here, and it's a wave traveling through air or something like that, cruising along. If I can take two pieces of that wavefront and beat them together and see a stable interference, then I have spatial coherence. So, classic example, I'll just put two slits here. I'll put a slit and a slit. So now I've got light coming out of there and light coming out of there. If down here I see this very nice stable pattern, and stable means I look at it and it sits there. It doesn't move. I have spatial coherence between these two. It means there's a fixed phase relation between these, and it's not changing in time. You know, the phase is rapidly changing because it's a wave, but the relative phase between the two is stable. So we say they are spatially coherent. If I did that with this light bulb here, if I took an aperture here and an aperture there, would you expect to see an interference pattern? No. Is there an interference pattern? There is. You know, there's light's always interfering, but it's just not stable. It's just washing out, changing all the time because I've got just two completely incoherent sources here. So they're interfering, but it's not stable. So fast you don't even see it. But if I do this and it just sits there, then it's stable. So an example. Thank you for this laser. When I look at this laser, if I can hold it steady, do you see it kind of sparkle? It looks like it's hitting a metal surface. I'll put it on the blackboard. Does it sparkle? Looks kind of metallic. I'll put it on metal. Does it look metallic? Notice wherever I put this laser beam, it has this kind of sparkle. Laser beams have this sparkle. And what it is because this laser beam is actually a spatially coherent field that's going along and it hits a surface, whatever that surface is. And the surface usually looks like crap, you know? But you've got light coming to your eye, and some of it's coming from here, and some's coming from here and here. And because these are all coherently illuminated, they interfere with each other because they have slightly different path lengths getting to your eye. And so this and this cancel. These two interfere positively, so they look bright. And the way you can tell, if you're blessed with glasses like me, take your glasses off, it still sparkles. You know, it's not because I have high resolution in my eyes. I see sparkle with or without my glasses. That's because the interference is happening on my retina. It's not. I'm not imaging. I'm actually getting interference on my eyeball. The pattern I see is clearly different from what you see. So that's an example of spatial coherence. When I've got a wave front, and across the wave front, the phase is stable. And the way you see that is interference. Just take 2 points, separate them. And if you keep seeing interference, it's spatially coherent. At some point, you don't see any more coherence or interference. That's the limit of spatial coherence. The other is temporal coherence. And that has to do with kind of the frequency of the beam. So if you have a laser beam, and it's cruising along, and I could make this, let's make this the z-axis. And this wave clearly was generated before this one was. So there's a time difference between these two because first this was generated, then many cycles later this one was generated. If I compare the phase here to the phase with this, so this represents a delta tau, and again look for interference. If I see interference, they're temporally coherent. Now, how do I do that? This usually involves an interferometer. So what you'll do is you'll take your beam and you'll beam split it. Send some of it that way, some of it this way. And we'll send this one down a long path, delay it, bounce it back. And this one may be on a short path. And then we bounce them back together. So that's an interferometer. This is called a Michelson interferometer. There's various types. But clearly I've got a delay here, not that, I've got a longer delay here than here. So I'm mixing light from here with light from here. And the longer I make this arm, the more time delay I'm introducing. And as I move, if I see a stable interference pattern here, I'm temporally coherent. And eventually there's so much phase noise that accumulates that you lose that coherence. But that's all temporal coherence is. So this is related in many ways to the delta omega of the source. If the line width of that laser is really sharp, the temporal coherence can be kilometers. If it's not very short, or if it's not very narrow, it can only be a short distance altogether. So having kilometers of temporal coherence, a coherence length of kilometers is not a big deal with the laser. Just the more narrow the frequency, the less phase accumulates over time, and the sharper it stays. So anyway, that's coherence. So spatial, this is for holography, things like that. Temporal, more for communication. But there are two types. They're distinct, but they all represent, is the phase stable between these 2 points? Does that make sense? All right. So that's, I think that's it for the definitions. So we're going to move on to the ray tracing stuff now, which I think is a lot of fun. So we want to start designing a laser. So we got to build some tools. Yeah.
Just before you erase that, For that graph, at 90 degrees, is this supposed to have zero reflection?
It has almost total reflection at 90 degrees. Yeah. So the reflection goes up to, it starts from some value and then it goes up to 100% at night. At grazing in angle, it's almost total.
Okay, so with that theta I, whatever, is it increasing down?
Yeah, this would be 0, 45, 90.
Okay, so
Yeah, that's what I'm doing there.
degrees, it's
Yeah. 0, 45, 90.
But if it's at 90, it's not gonna.
Okay, 89.9999.
Oh.
All right.
Okay. Yeah.
You know,
Oh.
but even 89 degrees, it's 100%, it's just grazing, it's grazing. So yeah. Okay, so we're going to develop a method for designing a laser cavity. It's called the ABCD law. And the ABCDs are matrix. We're going to use ray tracing to do this. I always found this rather remarkable. Here's the laser. This laser is a quantum device. It uses stimulated emission. It's unlike any sort of optic we have. And yet we're going to go back and do ray tracing, which is what you do for designing a lens on a camera. And we're going to use ray tracing to actually tell us what the beam looks like in the cavity and all this stuff. It's amazing story to me. I'm always amazed when I think about this because we're going to do very simple ray tracing. We're even going to make some crude approximations, and yet it gives this incredible tool, which is very accurate and tells us exactly what the beam looks like in the cavity. So this is a really neat, powerful tool. I'm done with this. I'm going to walk off with that. So thank you. So we're going to start ray tracing, and from this. I hope you're as awed as I am. I always find this just exciting. It's so neat that it works. So we'll go back and define a ray. Now we just started the lecture off by saying all beams diffract, and now we're going to talk about rays. Rays don't diffract. A ray is a real simple idea. We assume light is traveling in a straight line in a given direction, and that's a ray, and it just stays that way forever. We don't worry about diffraction, nothing else. We just assume it's traveling in a straight line. Ray tracing works so long as our beams are big. So if I have a camera, my lens is probably going to be 1 million wavelengths in diameter. That's huge compared to any sort of diffraction. So ray tracing works pretty good for classical optics. It's when our beam starts getting small, on the order of 100 wavelengths, the diffraction becomes an issue. So as long as we're big compared to the wavelength, ray tracing is okay. Anyway, we're gonna use this. So here's a ray. A ray is defined in our system. We're going to define what we call an optical axis, and this always confuses everybody. What the heck? What's an optical axis? I've got camera lens. I got a whole bunch of lenses. Light comes in here. My film's there. The center of that system is the optical axis. Which way is the light flowing? How am I trying to get my light through the system? That's the axis. I got a laser. It's got 2 mirrors. The beam goes out that way. That's the optical axis. Which is where is the light bouncing back and forth? That defines our axis. So I have to find, my system's always going to have some center line about which we'll do a reference of all of our positions. So I have some sort of axis, and I'm going to put a ray here. And I'm going to define the ray in terms of 2 parameters. One is, how far is it from the axis? And the second is, what is its slope? So you come up and you say, I've got a ray. It's at 3 centimeters at 22 degrees. I know everything I could possibly know about that ray. I know exactly where it is, and I know where it's going. So that's all I need to define a ray. So we're going to define this in terms of a vector. R prime. And that defines the ray. Now, I'm going to try and develop some techniques for evolving that array through a lens, off a mirror, translating in free space, that kind of stuff. So we're going to develop some matrices which describe this. And these matrices are called the ABCD matrix. If you've ever taken an optics course, Classic optics course, you'll see ABCD matrices. They're used all over the place for lens design and stuff. So we're going to use a form of them. So the next thing we want to do is develop some ABCD matrices to describe how these rays propagate. So the first thing we're going to look at is, okay, I know the ray right here. Let's call this Z equals 0. This is Z. How do I describe the ray at some distance Z? So I go down here, some distance Z. What is the ray? So this shouldn't be too hard. Clearly it started here, it propagates, now it's here. And the only thing that's happened is it's gone further from the axis. And how much further? Well, it's just very simple. I know that if I call this R1, I would say R2 must equal, this would be R1 plus, let's make this a distance L, just to be fun, L. It's going to be plus L times R1 prime. So it's the slope times the distance will give me this little rise here is R prime times L. So my new height is that. What's the slope? Same, yeah. So the slope is the same. So there's my new ray. So we just took a ray and propagated at a distance L. Now I want to do this in a form that looks like this. R2 prime equals A, B, C, D, R1 prime. So I want to describe this operation in terms of a matrix. And that's what the ABCD matrix is. Very clever name, right? ABCD. So let's look at this, and let's look at this, and let's just see if we can figure this out. So this is a very trivial example. But you can see right away that, okay, R2 prime equals R1 prime, so D must equal 1, C must equal 0. And then R2 equals R1, so A equals 1, plus L, R1 prime, so B must equal L. So just by looking at this, I'd say, okay, if I'm going to translate, I'll write this over here. If I'm going to do a translation, translate distance L, I can represent that by a matrix of 1, L, 0, 1. And now, whatever ray you give me, when I want to propagate at some distance, I'll just multiply by that matrix, and now I know what the new ray looks like. So now I can move rays around. Let's test this. I mean, this is really a trivial example, but if I were to go two distances, I've got my z-axis, and I'm starting here, and I'll go a distance L1, and then I'll go a distance L2. You would all say, just by inspection, you say obviously that this ray here, let's call it R3, is just going to be R1 plus R1 prime times L1 plus L2. And this is going to be R1 prime. I just added to the distance. But I can prove that if I do it with matrices. This really would represent, I would start with R1, R1 prime. First, I'm going to propagate a distance L1. Then I'm going to propagate a distance L2. Oops. And that's going to be my new vector. And if you do that, just run this through, you'll find this is going to be 1 plus L1 plus L2 times R1. You'll get the same answer. So it works out. Now, notice one thing. My ray's going this way. I multiply my matrices the other way. So first I hit L1, then I hit L2. So the first thing, you'll all do this, I do it. You'll see your optic system like this, and you'll drop down matrix L1, you'll do it this, and you'll multiply them in the backward order. So be conscious of how you're doing this thing. I'm starting with matrix, matrix multiplication works this way, unfortunately. So I start with my initial ray. I operate on it to get it to here. Then I operate it on to get it to there. And then I finally get R3. So very simple, trivial example, but that's how that works. So we will do this in optical cavities. I've got a laser cavity. It's going to have a mirror. It's going to have a gain medium. Maybe it's got a lens, and it's got another mirror. So I'm gonna propagate from this mirror to there. That's going to be L1. I'm going to cross an interface. That's going to be a matrix. I'm going to propagate another distance, L2. I'm going to cross another interface. I'm going to propagate another distance. So I'm going to use these length matrices all over the place when I build my laser. I get from surface to surface to surface mathematically by putting a matrix here. And that'll get my rays where they need to be. All right, well, that kind of illustrates the next problem. We got a lot of things in a laser we got to worry about. We got to come up with a matrix for a curved mirror, for a lens, for crossing a dielectric, who knows what else. Any sort of optical surface we go through, we want to characterize by an ABCD. So let's do a couple examples here. We got 10 minutes? Okay, so let's try and come up with an ABCD matrix for a lens. It's kind of fun to do these. But we'll step through it and you just see how to do it. I want to give you a sense of the flavor here. And there's nothing magic, it's just kind of common sense and just trying some stuff. But let's look at a lens and come up with the ABCD for a thin lens. So the way you do this is you better have some idea how a lens works, because you can't make an ABCD unless you have some idea about that. So here's my lens, here's my optical axis, and all lenses are characterized by a focal length. So it is a focal length. It also has aperture size and all that, but that has nothing to do with our matrix. All we need is a focal length for this system. So how does a lens work? Well, if you remember how lenses work, let's say if I bring in a bunch of parallel rays, and I focus the sun, these rays are coming in parallel, they will all converge at the focal length. So light coming in parallel on one side will converge all to one point, the conjugate point, and this distance is the focal length of the lens. Okay, now we know enough to figure this thing out. So now that you know how a lens works, we can try and figure out how to make these matrices. So what I want to do is figure out how to make some sort of, R1, R2 kind of connections. Now, we're going to use a thin lens, and that means we're going to assume there's no propagation between these surfaces. We're not going to worry about that. We'll do that in homework. We'll let you figure that out. Here we'll not. So our lens is going to look very thin, like that. And the matrix I'm going to create is going to relate the ray here to the ray there. It's not going to relate the ray here to that point. It's going to take me through the lens and nothing more. And if I want to get to here, I'll have to do a translation to get to here. But the ABCD I'm going to create is just going to tell me what happens. The ray hits here and goes to that lens. And now I know the ray on this side. So that's what I'm going to try and do. So here's my optic axis. I'm going to bring a ray in. It's going to leave. That's what that matrix will tell me. Okay, now we just figure it out. So I was like trying to come up with a couple just test rays. Let's just launch a ray in there, one that I know, and I'll write it down, and then I'll try and fix A, B, C, and D. So the simplest one is to, what I need to know is the slopes and the positions. So here's my lens. Here's my optic axis. The simplest one to me is come in with a parallel ray. I'm going to come in with something right here. So the initial ray has a height and no slope. And what I like about that is I know exactly where it's going. It's going to come through this ray, this lens, and it's going to shoot down here, and it's going to cross the axis a distance f away. Now I can figure out what the slope is, the exit slope. It's got a distance height here, f, r, and there's a distance f. So this slope is just going to be the tan inverse of r over f. So I know the slope. So now I can, okay, now what's the exit position? The beam came in at height R. What does it leave at? R. Does the height change at all? No. So the height doesn't change whatsoever going through this thing. So I already start to see some numbers here. So I know right away that A, no, just right here, A must equal 1 because remember we have R2 equals A, R1 plus B, R1 prime. So I know that R1 equals R2, so A has to equal 1. How about B? Can I take a guess on B? What do you think B is? 0. Yeah. Does it matter if this ray comes in like this or like that? It doesn't matter what angle it comes in, it always leaves at the same height on the other side. Does that make sense? So I can look at that and say, you know, B is 0. There's no question about it. We can go through the math and do it too. But you can sometimes you look at these things and say, ah, that's easy. Now I also know how to relate the exit angle, because I've got R2 prime equals CR plus D R1 prime. Now R1 prime is 0, so I know nothing about D. But look at this. I know C, and I've got a function here which depends on R. So I'm making progress. Now I'm going to make one more assumption. And this is where the optics people don't, and we do. We're going to assume that we're in what's called the paraxial approximation, which means our angles are not very big. We are pretty much parallel to the axis. Okay? What that means is tan theta equals theta. Now, if I do that, this becomes, that's a minus sign, minus R over F. The slope is downward. How do I do slopes? The ray is moving. It's moving along the axis. If it's moving down, that's a negative slope. If it's moving up, it's a positive slope. Okay? So I just ride with the ray. I'm going through here. I'm going down, negative slope. So we get rid of the tan. It's just R over F. So this is the paraxial approximation. And because we have little narrow beams and stuff, everything's kind of tight. They're not big dimensions here. So that works pretty well. So my exiting slope, this is R2 prime, is equal to minus R over F. So I look at this and say, well, C must be minus 1 over F. And all that leaves is D. I have no idea what D is, because I have no way to test that. But I've got 3 of them already. Make sense? So we're just playing around. So I have to shoot a second ray to figure out D. And again, I got to look at this and say, okay, I need one which I know. And then once I know it, I can go through and calculate it. And what I usually do, I just reverse the thing. So I've got a lens like this. Here's my optic axis. What if I start at the focal point? I'll come out parallel. What I like about this is I know it hits at a position R. It has a slope of R over F. That's R1. So I know its height and its slope on input. Its exit, same height, 0 slope. So I know R1, I know R2. And so now I just look at my equations. I say, okay, let's see if I can work this out. So I know that R2 prime equals, I already figured one of these things out, minus 1 over F R1 plus D times R1 prime. So I look at this. I said, well, R2 prime equals 0. And R1 prime equals R over F. So this becomes, I'll just write it again, minus 1 over R1 plus D times R1 over F. And this must equal 0. So I look at that and say, you know, D must equal 1. And so now I'm done. And now I've got the ABCD matrix for a lens. Yeah?
I'm sorry, why did you make that negative?
Here's my slope here. I came in with no slope, and I left like that, and it's a negative slope. So my input was 0, my output was minus r over f, so it's a negative slope. Yeah. So there we are, and that's how you go about doing this. Just kind of run through these things, and we'll do a one or two more, then I'll let you play with it. But it's basically just look at it, mess around, figure out A, B, C, and D. You got your matrix. Pretty simple stuff. Okay. All right. So we have Monday off. That's great. So I'll see you Wednesday, I guess.